Okay, we are on vapor and partial pressures, and we're going to take a look at the warm-up. It says, use the box on the left to sketch a molecular representation of a sample of clean air. Remember that it's roughly 80 to 20 parts nitrogen and oxygen. Use the box on the right to do the same for moist air. The box will show what happens when the humidity is high. Okay, so what I'm going to do is I'm going to use nitrogen as two circles attached to each other, and then oxygen will just be two unfilled circles. So I'm going to have 8 of these nitrogens. And then I'm going to have 2 oxygens. And this is clean air. And then this is moist air, which is going to need to have water. So I'm going to use this symbol to represent my water molecules. Keep Avogadro's hypothesis in mind as you do this. Equal volumes of gas should contain equal numbers of particles, which mine do. A, are these accurate representations of what the gas samples actually look like? Explain your answer. Well, I would say no, because gas particles wouldn't be visible. Because gas particles are so small that they're not going to be anything more than just pinpoints in space. And they're occupying a very small amount. We often say that it's a negligible amount of the overall container volume. And they would be constantly moving. B, what percent of the pressure exerted by particles colliding with the walls of the box on the left is due to oxygen gas? How does the pressure exerted by oxygen, called the partial pressure of oxygen in the box on the right, compare with that in the box on the left? Explain. Well, the partial pressure of oxygen in clean air is going to be 20% because I've got 2 of these oxygen gas particles, 1, 2, 3, 4, 5, 6, 7, 8, right? The total is 10 if you add them up. So 2 out of 10, that means it's going to be 20% is going to be the partial pressure of oxygen in clean air. In moist air, it's going to be about 10%, right? It's going to be less than that. Why do meteorologists say the barometer is falling when it is about to rain? Well, as water molecules in moist air condensate and rain, the air pressure exerted by the water molecules are lost, and the air pressure readings on the barometer will fall. Let's go to the next page and take a look here at vapor pressure. So you know that puddles of water eventually evaporate, even though the temperature is below the water's boiling point. And some of the molecules have enough energy to escape from the surface of the water and enter the gas phase. And that's what this figure is showing us here. And over time, the entire puddle of water evaporates even though we're at room temperature. So here you'll notice that the area under the curve to the right of the minimum escape kinetic energy represents the particles with enough energy to evaporate. So at my lower temperature, which is the blue line, this area underneath this, this dashed line here to the right, that's how many particles have enough energy to evaporate. But as the temperature increases, look at how many more have enough energy to evaporate. And we use the term vapor for the gaseous portion of a substance that's present above the liquid phase of that substance. So here, I'm looking at the pressure that's exerted by the vapor above itself. So here, for instance, I have water in this upside down bottle. Over here, you'll notice that I have, and I'm collecting a gas is entering in here, and it's going up through the water, and it's going to fill this empty space above it. So now the water level has come down, and I have gas and water in above the liquid. Now, the water vapor is exerting a pressure, and so is the other gas that is over the water, and that added together is the total pressure. And the vapor pressure of water is what we call it when we're referring to the pressure that is exerted by the water above itself, or by a liquid above itself. So vapor pressure is actually explaining why we can smell some liquids, like nail polish remover, which is acetone, or rubbing alcohol, or black licorice solid. Like, this is why we can smell it sometimes, because the vapor pressure of a substance depends on a couple of things. The first thing is it depends upon its structure. And the second, it depends upon the temperature. And at a certain temperature, there's a maximum value that the vapor pressure can reach. And every single liquid has a vapor pressure. Here you'll see in this table that we have the vapor pressure in kilopascals at various temperatures for water. You'll notice as my temperature is increasing, as I go down, the vapor pressures are also increasing. From this information, we come to the definition for boiling point of a liquid. The boiling point of a liquid occurs when the vapor pressure equals the atmospheric pressure. So here, you'll notice that in this figure, 760 torr, which is right here, that's this dashed line going across. That is showing you the boiling points of various liquids. So here, diethyl ether, 34.5 degrees Celsius at atmospheric pressure at sea level. That's its boiling point. Ethanol is 78.5 degrees Celsius here. Water is 100 degrees Celsius. So these are the boiling points. And these are the temperatures where the liquid's vapor pressure, abbreviated V period P period, reaches 760 torr. Let's talk about boiling and atmospheric pressure. Boiling points change with atmospheric pressure. So as the atmospheric pressure decreases, the boiling points become lower and lower. For instance, in Denver, Colorado, the boiling point of water is 94 degrees Celsius. So it takes longer to boil an egg at higher altitudes because the water is boiling at a lower temperature. Here we have the atmospheric pressure is 620 millimeters of mercury in the Smoky Mountains National Park. It's 500 millimeters of mercury at Mount Rainier in Washington, and at Mount Everest it's 270 millimeters of mercury. So the atmospheric pressure as I increase in altitude is decreasing. The corresponding boiling point of water is also decreasing as the atmospheric pressure decreases or as the altitude increases. Let's talk about intermolecular forces and boiling point. The reason liquids have different boiling points is because of intermolecular forces. These are things like London dispersion forces, which exist in nonpolar substances, or everything really, but nonpolar substances only have LDF forces. Dipole-dipole forces exist in polar substances. Hydrogen bonds are a special dipole force, which only exists in polar molecules that have HF or NH or OH bonds, and they're the strongest of the three intermolecular forces. The stronger the intermolecular force, the fewer atoms that have enough energy to overcome the attractive forces between them and escape into the gas phase. So here you'll notice that in this table I have diethyl ether, ethanol, water, and mercury. Now, water has 2 hydrogen bond locations. Ethanol has 1 hydrogen bond location. Diethyl ether is a slightly polar molecule. And then mercury has metallic bonding. And those, this really has strong intermolecular forces. So the intermolecular forces are increasing as you go down this table. You'll notice that the vapor pressure is decreasing with increasing intermolecular force strength. So that means it gets harder and harder to get these substances into the gas phase, or the atoms don't have enough energy to overcome the attraction between them to get into the gas phase. That's why the vapor pressure is decreasing. And you'll notice that the boiling point is increasing as my intermolecular force strength increases. Let's take a look at the quick check on the next page. A bell jar is placed over a beaker partially filled with water. What will happen to the height of the water in the beaker over time? Explain why. Well, it will decrease because some of the water evaporates. And some of the water evaporates because of the vapor pressure that it exerts. So vapor pressure causes water to evaporate. Letter B. If the temperature of the system is increased, how will the answer to part A change? Well, the height of the water decreases more and becomes constant faster than it did in part A. So an increase in temperature is actually going to provide more kinetic energy for the molecules to escape into the gas phase. C. If the system is transported to the top of Mount Rainier in Washington, where the atmospheric pressure is only 500 millimeters of mercury, how will the answer to part A change? Assume temperature remains constant. Well, the atmospheric pressure at sea level is 760 millimeters of mercury. So even though this is decreasing to 500 millimeters of mercury, there's no change in the height of water because a change in atmospheric pressure affects the boiling point, not vapor pressure. Vapor pressure depends on the temperature and the structure of molecules. Number 2. A bell jar is placed over the 2 beakers shown. As Acetone is a low polarity volatile liquid. How will the vapor pressure of the water inside the bell jar compare with the vapor pressure of the acetone after 1 hour has passed? Explain your answer. So for this one, you can scan the QR code with your phone and go over the answer. Let's take a look at the next page. Let's talk about Dalton's Law of partial pressures. Dalton did a series of experiments, prepared various gases, collected them in a collection jar by displacing water from the jar using a pneumatic trough. And this right here is where you have a reaction occurring that releases a gas. It goes into the tube goes under the water, it bubbles up over the water, and is collected here above the water. That's why it says gas 1 plus the water vapor. Okay, so anytime you're collecting gas over water, it's going to be a mixture of the dry gas and the water vapor itself. So this is represented by the total pressure is going to be equal to the pressure of gas number 1 that you're collecting plus the vapor pressure of water. So this right here is the vapor pressure of water, which is dependent upon temperature, which is why they will often tell you the temperature that the reaction is taking place, and you will reference back on a previous page in the table the appropriate vapor pressure of water value that you want to use for that experiment. Now, the contribution made by each gas is known as partial pressure. So the partial pressure of gas 1 and the partial pressure of water, those added together give you the total pressure. This is known as Dalton's Law of partial pressures. This equation is just a variation of Dalton's Law of partial pressures. So Dalton's Law of partial pressures is where you add the pressure of each gas in a mixture together to get the total pressure, which is shown for you here. You can have 2, 3, 4, 5, 10 gases in a sample, it doesn't matter. This is showing you the pressure of gas A and B and C. The partial pressures of each added together give you the total, and that is Dalton's Law of partial pressures. If we take a look at the next page, at the practice problems here, it says 2 gases are combined sealed in a 2-liter container. The 3 liters of argon gas and the 1 liter of xenon each exert an atmosphere pressure on the walls of their container. Calculate the partial pressure of each gas in the 2-liter container. Well, if I look at the ratios, 3 liters of argon gas in a 2-liter mixture is going to be 1.5 atmospheres for argon. If I'm talking about xenon, I have a liter of xenon in a 2-liter mixture. This is going to be 0.5 atmospheres for xenon. What is the total pressure in the 2-liter container? Well, 1.5 atmospheres for argon plus 0.5 atmospheres for xenon is going to be 2.0 atmospheres for the total pressure. If I take a look at problem number 2, for this one, you should scan that QR code with your phone and go over the answer. Let's talk about collecting gas over water in a little bit more detail. Remember, I gave you an equation for collecting a gas over water. The total pressure equals the pressure of the gas that's being collected plus the vapor pressure of water at that temperature. Here we've got 0.65 grams of powdered zinc in this flask reacting with sulfuric acid to produce hydrogen gas. And the hydrogen gas is coming up here through this tube, and then it's traveling under the water and it's bubbling up and be collected over water, which means you will have hydrogen gas plus you will have water vapor mixed in with it. Now, they want to know at 20 degrees Celsius, the reason they gave you this temperature is so that you can look back at the previous page to get the vapor pressure of water at 20 degrees Celsius. And the vapor pressure of water at 20 degrees Celsius is 2.34 kilopascals, okay? And you're going to calculate the pressure of the dry gas. So I've got the partial pressure of hydrogen gas and then the vapor pressure of water added together to give me the total. They told me that the pressure in the lab is 101.3 kilopascals, so that's my total. I need to solve for the pressure of the dry gas. I substitute everything in, subtract 2.34 from both sides. You're going to end up with 98.96 kilopascals for the partial pressure of that dry hydrogen gas. For practice problem number 2, on the next page, you're going to scan that QR code with your phone and go over that answer. Okay, now let's talk about using mole fractions to calculate partial pressures. So here, mole fractions are going to be where you have the moles of one component in your sample divided by the total mole. So this right here, mole fraction, is multiplied by the total pressure to give you the pressure of one component in your gas sample. So if we go to the next page to apply this, we're going to take a look here at these practice problems. We have a mixture of 0.5 moles of hydrogen gas, 0.25 moles of oxygen gas with a total pressure of 6 times 10 to the first kilopascals. What is the partial pressure exerted by each of the gases? So the partial pressure of hydrogen gas is going to be the total pressure times the moles of hydrogen over the total moles. So this is going to be 6.0 times 10 to the first kilopascals times 0.5 moles of H2 divided by 0.7 total moles in the sample. This is going to be 40 kilopascals for the partial pressure of hydrogen. The partial pressure of oxygen is going to be the total pressure, 6.0 times 10 to the first, times 0.25 moles of oxygen over 0.75 moles total, which is 20 kilopascals. You can scan the QR code for problem number 2 with your phone and go over it on your own.